Let's start this journey exploring one of the most fascinating and captivating phenomena in the cosmos: black holes. These celestial wonders have an extraordinary gravitational force of such magnitude that not even light, with its remarkable speed, can escape its grip. Scientists speculate that within our vast Milky Way galaxy, there could be over 100 million black holes, hiding stealthily and challenging our efforts to find them. However, nestled at the very core of our Milky Way, we see a supermassive black hole, known as Sagittarius A. This massive celestial structure, a true giant in astronomy, has a mass of approximately 4 million times that of our radiant Sun. Moreover, it is located around 26,000 light-years away from our Earth, as stated by the National Aeronautics and Space Administration, NASA. It is within the depths of this cosmic abyss these black holes are said to form, through two distinct channels, each with its own mystical story. According to the tale of the first cosmological pathway, these black holes are born from the remnants of massive dying stars, representing the cycle of life and death that envelops the celestial bodies. When stars whose initial masses exceed the threshold of 8 to 10 times that of our Sun exhaust their hydrogen fuel, they succumb to a cataclysmic explosion, leaving behind a compact and dense object that we know as a black hole. These remnants black holes possess a mass that exceeds that of Earth's Sun by orders of magnitude. However, not all stars are destined to fade totally from cosmic history. Stars with lower birth masses leave behind their remnants, known as neutron stars or white dwarfs. Another enthralling path opens up in front of us, one that leads to the direct collapse of gaseous stuff, an intriguing process that gives birth to black holes of massive proportions. These black holes can have masses ranging from 1 billion times that of our Sun to an incomprehensible hundreds of thousands of solar masses. This cosmic channel delicately deviates from the actual course of star formation, unfolding its fascinating ballet during the universe's early years while concurrently sowing the seeds of black holes that define the cosmic tale. However, not all black holes die indefinitely. Instead, it is theoretically predicted that these ethereal entities will gradually vanish into the cosmic ether over long periods. Their descent into oblivion is imperceptibly slow, inspiring contemplation and amazement as we consider the ethereal dance of existence amid the universal symphony. The extraordinary growth of black holes is caused by their interaction with matter that occurs to cross their cosmic route, becoming entangled within the web of their gravitational attraction. Stephen Hawking, the great physicist, revealed to the scientific community through his profound discoveries that black holes tend to radiate energy, announcing their gradual shrinkage. Quantum theory suggests a world in which virtual particles constantly materialize and dematerialize, flickering in and out of existence with ethereal grace. This cosmic interaction of ephemeral existence produces pairs of particles and antiparticles poised on the brink of creation and death. However, something strange is happening. Instead of a brief encounter between particle and antiparticle, one of the twins may succumb to gravitational forces, falling into the abyss of the black hole, while its former companion, free from the gravitational forces, will be flung into space. But first, let us clear up this popular cosmic confusion. Although it sounds similar, black holes and wormholes are not the same bodies. Wormholes can be seen as tunnels that create momentary links between different places in the fabric of space and time, beyond the limitations of conventional cosmic geometry. It is a high possibility that the abysses beneath black holes contain wormholes, which could, conceivably, become portals to other realms, even with alternative universes beyond our human perception's cosmic horizon. Next on this journey, our attention is now drawn to the mystery birth of our cosmic friend, the Moon. A scientific theory tells the story of a massive cosmic collision, a captivating spectacle that occurred billions of years ago. According to this enthralling story, a cataclysmic event echoed across the cosmos roughly 4.5 billion years ago, giving origin to the moon that graces our night skies. The giant impact theory proposes a historic collision between our young Earth and Theia, a celestial body similar in size to Mars. This dance between the two bodies ended in an ejection of cosmic debris into space. This ethereal debris, driven by the powerful force of gravity, merged and fused through time, giving birth to the beautiful moon that we see in the night sky. Now let us delve into the metaphysical perspective. In the grand story of the universe, every event is intricately connected and resonates with the fundamental principles of quantum mechanics. The birth of the moon, too, finds its roots in this web of interconnectedness. We see a cosmic ballet of entanglement, considering the fascinating concept of quantum entanglement in which particles become connected and their fates are irrevocably linked, regardless of the vast distances that separate them. Earth and Theia engage in a sublime dance within this enchanting choreography, each movement led to the interaction of quantum forces. The vibrations and fluctuations of quantum existence set the stage for the majestic collision of Earth and Theia. As they merged and intertwined, their quantum information and energy intertwined as well, leading to the birth of our moon. Let us turn our attention to star and planetary formation and evolution. Stars, blazing giants of plasma, burn with fervor, fueled by the violent fusion burning at their stellar cores. These giants are born from collapsing gas and dust clouds in the vast expanses of interstellar space, etching their existence into the cosmic stage. Their longevity, which can range from millions to billions of years, is determined by their mass and composition, which must be delicately balanced between gravitational forces and the eternal celestial inferno that consumes their stellar core. Stars explode in supernova events, or in some cases, give birth to mystic cosmic creatures known as black holes as they die. These stars create almost all the elements heavier than hydrogen and helium, filling the universe, for example, gold, oxygen, and iron. They also provide light and energy, the building blocks that allow life to exist. Planets are celestial bodies that revolve around stars, and they can be classified into two main types: rocky planets and gaseous planets. These planetary entities take shape from the accumulation of matter in the disks surrounding young stars. Planets also come in different sizes, shapes, chemical makeup, varying temperatures, gravitational forces, magnetism, and rotation. Planets also have incredible features like moons, rings, asteroids, and comets, and more intriguingly, they can provide a habitat for life, ranging from simple bacteria to extraterrestrial beings. The formation and development of stars and planets are influenced by numerous factors, including magnetic fields, radiation pressure, gravity, turbulence, and feedback mechanisms. The impact their environments, such as galactic spiral arms, molecular clouds, and supernova remnants have on them also plays a significant role in shaping their evolution. To understand the mystery behind the evolution of humans, we must first comprehend the formation of stars and planets in the universe. Yet, within the cosmic theater, stars also possess a finite lifespan, and their death is just as spectacular as their birth. A star initiates its journey when hydrogen fusion ignites within its burning and dense core. Once this process begins, a remarkable interplay of forces begins. The immense gravitational pull coming from the star's entire mass tries to compress it into a minuscule point. However, the energy unleashed by fusion exerts an outward pressure, delicately balancing the inward force. This equilibrium can persist for millions or even trillions of years. Small stars have an astonishingly extended lifespan. Due to their tiny size, they require little energy to counteract the gravitational pull, thus conserving their hydrogen reserves. Moreover, the atmospheres of these stars facilitate constant circulation, drawing fresh hydrogen from the outer layers into the core, where it fuels the ongoing fusion process. A red dwarf star can peacefully sustain hydrogen fusion in its core for trillions of years. That is quite an impressive feat. As these small stars age, they gradually grow brighter and brighter until they gradually fade away, transforming into inactive remnants composed of helium and hydrogen, quietly drifting about in the vast expanse of the universe. On the other hand, when massive stars meet their demise, the event is far more tumultuous. Due to their large size, fusion reactions within these stars must occur at a fast pace to maintain a delicate balance with gravity. Despite their large mass compared to the red dwarf star, these stars have considerably shorter lifespans. Within a mere few million years, they burn out and die. It might look like a lot of time, but in astronomical years, it is a short amount of time. However, the death of massive stars happens with a spectacular grand finale. Their large size enables them to fuse not only hydrogen, but also helium, silicon, oxygen, carbon, magnesium, and a considerable number of other elements on the periodic table. Towards the final stages of their life, these giant stars form an iron core, marking the end of the fusion processes and the beginning of their death. The material surrounding the iron core compresses the core, but unlike other fusion processes, iron fusion does not release so much energy to counter the inward pressure. The core contracts to such mind-boggling densities that electrons are forced into protons, transforming the entire core into a massive ball of neutrons. Temporarily, this neutron core resists the crushing collapse, triggering a cataclysmic supernova explosion. A supernova releases more energy in a week than our Sun would emit over its entire lifetime. The expelled material and shockwave from this explosion carve out cavities in the interstellar medium, disrupt nebulae, and even propel matter beyond the confines of galaxies themselves. Our last stop on this cosmic journey is the periodic pulsing of pulsar stars. Pulsars are the extraordinarily dense remnants left behind when massive stars explode as supernovae. Pulsars are rapidly rotating neutron stars that emit electromagnetic radiation in the form of a focused beam, very similar to the sweeping motion of a lighthouse beam across a shoreline. To comprehend the birth of a pulsar, you must first learn about the formation of a neutron star. When a massive star, with a core approximately 1 to 3 times the mass of our Sun, undergoes a supernova explosion, the resulting remnant is a neutron star. While most of the star's material is ejected into space, the core implodes. Protons and electrons within the star merge to form neutrons. As the star shrinks while retaining its mass, it begins to rotate rapidly. Although the first pulsar was discovered in 1967, scientists have grappled for decades to unravel the mechanisms behind the pulsating behavior and the occasional cessation of this pulsing activity. However, in 2008, a pulsar abruptly ceased its pulsations for about 580 days, allowing scientists to deduce a connection between the on and off periods and the gradual slowdown of the star's magnetic currents. And that brings us to the end of this video. Let us know if you enjoyed this video, and as always, keep exploring.